Okay, so for today's lesson, we're going to look at the last two of our gas laws. We're going to start off with Charles's law, and then the last one we do will be Guy Lussac's law. But let's go ahead and start off with Charles's law. And Charles's law, we keep pressure constant. And what will be direct relationship is between temperature and volume. So as the temperature increases, the volume will increase. As the temperature decreases, the volume will decrease. Okay, and why? What's going on here that causes this relationship? Well, when you have higher temperatures, the gas molecules move faster. They're going to collide with the walls of the container more frequently and with more force. So if you have a container that's flexible in volume, let's say like a balloon, then that volume is going to increase in order for the pressure to remain the same. Now, Charles discovered that the volume changes by 1 over 273 of the original volume for each Celsius degree. And this happens at a constant pressure and at an initial temperature of 0 degrees Celsius. So this is how Charles discovered the conversion between Celsius and degrees Celsius and kelvins. That's why we add 273. Nowadays we know it's a little bit more precise than that. Nowadays we know that it's 273.15 is the conversion factor between Celsius and kelvins. Gas volume and Kelvin temperature are directly proportional to each other at constant pressure. So this gives us the direct relationship. Notice that we are using Kelvin temperature. So when you are doing Charles's law, you do need to have the temperature in kelvins. So if in the problem it's given to you in degrees Celsius, you need to go ahead and convert that using that 273.15 to convert those degrees Celsius into kelvins. Volume, on the other hand, once again, it can be in milliliters, it can be in liters, just as long as both volumes are in the same unit. All right, so let's look at the graph. And we see that the temperature is our independent variable, so it's going to be on the x-axis. And our volume is the dependent variable, which will be on the y-axis. And we know it's a direct relationship because look at the shape of our line. It's that nice straight diagonal line. So as the temperature increases, we see the volume increase. Remember from when we did Boyle's law, we had a much different shape. We had a shape that looked that was curved because of that inverse relationship. So that as one was increasing, the other one was decreasing. And so we got this odd curve shape when we were doing Boyle's law. But Charles, direct relationship, so we see that nice straight diagonal line increasing as you move to that top right corner of the graph. All right, so let's look at some real life examples of Charles's law. Yeast in bread baking. The yeast produces carbon dioxide gas, which is what causes the bread to rise. The volume of the CO2 increases by baking the bread in a very hot oven. You'll notice if you've been baking any bread during this quarantine that your oven is usually at a very hot temperature, 400, 425. And that hot temperature is what's going to help to increase the volume of that CO2 gas that's being put out by that yeast, and which allows you to have that nice light fluffy bread or biscuits. Another example of Charles's law is how your car engine works. So if you can see, I'm going to scoot this over a little bit. If you can see in this picture, what we have here is a cylinder. Let's see. And it's kind of complicated, and it happens really fast. So right here, in here, we have two little valves. Okay, so I'm just going to mark them with a V. Okay, notice as one valve opens, the other one's closed. Well, why is it opening? What's coming in here into the cylinder? This is where a little bitty bit of gas is going in there. Now, notice that the piston is all the way down. Now, when the piston comes up, the volume, that decreases the volume. Then this part right here in the middle, that's your spark plug. And that's going to create that little bit of electricity. And when we have that little bit of hydrocarbon, gasoline, and that spark, and of course there's oxygen in here as well, we're going to have a combustion reaction. So here you go. In the next picture, we see that combustion reaction. What is one of the products of combustion reaction? Well, CO2 gas and also heat. So now we're seeing that that temperature inside that piston is going to be increased. With that increase in temperature is going to be an increase in volume. That's going to push this piston down. Okay, and at the very end, the other valve over here on this side opens up so those gases, that CO2, can be released from the cylinder. Now, what is all of this connected to? This picture here. So you have to kind of picture everything that I've just mentioned to y'all happening very quickly and all almost practically at the same time. This is all connected to your crankshaft. So this down here would be the crankshaft. So what these pistons are doing is actually providing the motion to the crankshaft, which eventually, okay, it's a little bit more complicated than how I'm describing it, but this will eventually give your car, this crankshaft will eventually give motion to your tires, which then gives motion to the car. All right. Now, one of the things also, just so you know some more about how your car works, when you put oil in your car, what are you doing? What is the oil used for? The oil is used in these pistons here because remember, like I said, this is happening incredibly fast. And so you don't want a lot of friction to build up in between the walls of your cylinder and this piston over here. So the oil is used to keep this greased so you have a very smooth movement here with as little friction as possible. This is why you don't ever want to let your car run out of oil, why it's so important to change your oil, because if this gets overheated and burns up, the whole engine becomes messed up, and it's a very expensive repair. So oil is important in order to keep these pistons moving well so that we can see Charles's law at work in your car engine, all because of some gasoline, a combustion reaction that happens from the gasoline and the spark plug. All right, now here comes something else that's also very important, and that is the formula. So the formula for Charles's law is the volume of the initial volume over the initial temperature equals the second volume over the second temperature, or the final volume over the final temperature. Now, for some of y'all, you may be looking at this formula and you're starting to hyperventilate and freak out because it's a fraction and fractions just bother you to no end. And if you are one of those people, I do have something that I'm hoping will help you feel a little bit better about Charles's law. So if fractions bother you to no end, there's another way that you can write Charles's law, and it's this. You can say that volume 1 times the temperature 2 equals volume 2 times temperature 1. Okay? So I'm just going to put a little or sign right there in between the two. And it is completely up to you if you choose to learn Charles's law like you see in yellow on the page, or if you choose to learn Charles's law the way I wrote it on the right in green. Now, with that being said, most of your textbooks, most of your YouTube videos and websites are going to write Charles's law as you see it on the left. But once again, if that fraction just really scares you, you do have another way that you can learn and memorize Charles's law. And yes, I do think that you should memorize these different formulas. All right, so once again, if you are given 3 of the 4 values, you are required to be able to find the value of the 4th one. And as I said before, don't forget, this is important over here, that temperature must be in kelvins for Charles's law problems. Let's go ahead and try one of these out and see how it goes. Let me scroll up the screen. Okay, so a gas takes up a volume of 17 liters and a temperature of 299 kelvins. If I raise the temperature to 381 kelvins, what is the new volume of the gas? So as always, ladies, let's start off by writing down all of our knowns and unknowns. So our knowns. So we have the initial volume, or volume 1, of 17 liters. We're also given the initial temperature, or temperature 1, as 299 kelvins. And then we're also told that temperature 2, the final temperature, was raised to 381 kelvins. And so that means we must be solving for volume 2, which will be in liters. So once again, I'm going to go ahead and work this problem using both of those equations side by side so you can see them. And let's do this. I'll work this one in blue. So if we have volume 1 over temperature 1 equals volume 2 over temperature 2. So that is 17 liters over 299 kelvins equals V2 over 381 kelvins. So this is going to end up being 381 kelvins times 17 liters over 299 kelvins, and that's going to equal our V2. And then once again, ladies, go ahead and punch and crunch. Put that in your calculator. And first of all, before we talk about the answer, let's talk about significant figures. So let's see, we have 3 significant figures here, 2 here, and then we have another 3 significant figures here. So our final answer is going to have 2 significant figures. So when you put all that in your calculator, you probably came up with, or hopefully you came up with 21.6 and lots of things past the 6. Once again, we're going to underline our second significant figure, look behind. That 6 is going to increase the 1, so that's going to become 22 liters equals your second volume. And as always, I'm going to box my final answer. All right, so let me scroll this over just a bit more, and let me go ahead and work the problem again. And this time, let's do it, find a nice color here, and let's work it using the other formula. So the other formula is volume 1 times temperature 2. So notice that it's different ones. So we have the initial volume times the final temperature, and that equals the final volume, volume 2, times the initial temperature, temperature 1. So that's going to look like this: 17 liters times 381 kelvins equals volume 2 times 299 kelvins. So we're going to divide by 299 kelvins. So look, ladies, at this point, in case you haven't noticed, this part looks just like what I have going on the left-hand side. Okay, so this is why it is fine to use this formula. There's nothing really magical going on here. This is just algebra. This is me having taken the original fraction and gone from dividing to multiplying, and that's why it's V1 times T2 equals V2 times T1. All right, let me go back to that orange. And once again, if you plug and chug, you're going to come up with that 21.6. Underline, look behind. So I'll give you 22 liters equals your final volume. All right, so that is Charles's law. So one more time, just in case you need to look at this. Charles's law, we're talking about a direct relationship between volume and temperature. Direct means that as the volume increases, as the temperature increases, the volume increases. The graph of Charles's law will form this nice, pretty straight diagonal line because of this direct relationship. We see temperature is on the x-axis and volume is on the y-axis. Don't forget that temperature has to be in kelvins. It cannot be in degrees Celsius when we are solving for Charles's law. And also, don't forget, you have two different variations of the formula for Charles's law. You can either use this formula or you can use this formula. Okay? It is completely and totally up to you. And then let's see here. All right, so that's Charles's law. Let's go on to Guy-Lussac's law, and let's see what's happening there. So now for Guy-Lussac, we have a constant volume, but we will see that as the pressure of a gas increases, the pressure of a gas increases with increasing temperature. So once again, we see a direct relationship between pressure and temperature. Temperature increases, pressure increases. Temperature decreases, pressure decreases. And this one is a little bit more vice versa because you can also increase the pressure, which will also increase the temperature. For Charles's law, usually what you're going to see is that as you increase the temperature, that's going to cause the volume to increase. We usually don't just see a volume increasing causing a temperature increase. While as Guy-Lussac, we can work the sentence either way. The pressure increase will cause a temperature increase, or a temperature increase can cause a pressure increase. All right, so gas pressure is the result of collisions of molecules with the container walls. The energy and frequency of collisions depends on the average kinetic energy of the molecules. And don't forget, average kinetic energy, that is the definition of temperature. Because the Kelvin temperature depends directly on average kinetic energy, pressure is directly proportional to Kelvin temperature. So at a constant volume, the pressure of a gas increases with increasing temperature. Gas pressure is the result of collisions of molecules with container walls. Let's see, because the Kelvin temperature depends directly on average kinetic energy, pressure is directly proportional. So once again, because of this direct relationship between temperature and pressure, we once again see that we have a graph that makes a nice, pretty, straight diagonal line that increases as you move to the top right of your graph. Temperature is on the X, pressure is on the Y. And let's look at some real life examples of Gay-Lussac's law. Aerosol cans. So if you've ever looked at an aerosol can, maybe for hairspray, shaving cream, all of them are going to tell you not to heat the can. Why? When an aerosol can is heated, the particles in the can gain kinetic energy, which then causes them to move around faster and have more collisions. More collisions without any more space equals more pressure and eventually an explosion. So this is why you don't ever heat up any kind of aerosol can. Like I was saying, whether that is hairspray, shaving cream, dry shampoo cans. All of those aerosol cans should never be put under a ton of heat because they will eventually explode. Because the can is rigid. The volume of the can is rigid. It can't increase, so that's why you get that explosion. Now, a pressure cooker is another example of something that works under gas laws. According to Gay-Lussac's law, as the pressure increases, so does the temperature. An increase in temp should decrease your cooking time, which is why food cooks so quickly in a pressure cooker. So once again, as you increase that pressure inside of the pressure cooker, you are going to increase that temperature. And of course, as you increase the temperature, that means your food is going to cook much faster. And for any of y'all whose parents have an Instapot, you know that food can cook really fast in one of those. And really, an Instapot is nothing more than a pressure cooker. All right, so let's look at our formula for Gay-Lussac's law. Once again, yep, we have another fraction here. So just like before, if for some reason fractions just cause you to start feeling lightheaded and hyperventilating, you can once again change this. So you can write Gay-Lussac's law as P1 times T2 equals P2 times T1. Okay, so either or, okay, it doesn't matter which one you want to learn. I will say whichever one you choose, you should go ahead and stick with for all of your assignments, all of your practice, including what you do on the test. I do not recommend that you flip-flop between these two ways of writing Gay-Lussac's formula or Charles's law formula. Pick one and stick with it. Now, something else that I needed to talk to you about, and that was this idea of STP. You maybe have heard of STP before, but didn't know what that stood for. STP stands for standard temperature and pressure. Your standard temperature is 273, and I should have written that as 273.15. kelvins, and your standard pressure is 1 atmosphere. Once again, just to make life probably a little bit easier in terms of significant figures, you can write that as 1.0 atmospheres. So you may see in some of the problems that you have to do for homework or any of your worksheets, them talking about standard temperature or standard pressure, or saying that an object is at standard temperature and standard pressure. It is at STP. And so when it's going to say those things, but it's not going to give you the numbers. So what does that mean? That means, yep, you're right, you have something else that you need to memorize. All right, so once again, STP, that is going to be 273.15 kelvins and 1.0 atmospheres. All right, let's go ahead and work another example problem, and this time we're going to do an example problem for Guy-Lussac's law. The problem states that a gas that has a temperature of 45.0 degrees Celsius at an unknown pressure and has its temperature decreased to 35.0 degrees Celsius. And if I measure the pressure after the change to be 2.0 atmospheres, what was the original pressure of the gas? So once again, we're going to start off by writing down our knowns and our unknowns. So we're going to start off with a temperature of 45.0 degrees Celsius. And the temperature is then decreased to 35.0 degrees Celsius. If you measure the pressure after the change, okay, so that is going to be pressure 2, and it is 2.0 atmospheres. And what you need to solve for, your unknown, is going to be that original pressure, that pressure 1. Now notice that for this problem, you were given the temperature in degrees Celsius. So you need to go about converting that temperature into kelvins. So what I would recommend, pick a different color ink and go ahead and put that in there. Once again, punch and crunch. All right, so your temperature 1 is going to be 318.15 kelvins. And your temperature 2, that's going to be 308.15 kelvins. All right, so now let's go ahead and worry about writing our formulas for this. And once again, I'll do the same thing where I will work it using both formulas. So your first one is pressure 1 over temperature 1 equals pressure 2 over temperature 2. So remember, pressure 1, that's what we're solving for. And temperature 1 is going to be 318.15 kelvins. Pressure 2 is 2.0 atmospheres. And temperature 2 is 308.15 kelvins. Okay, so pressure 1 is going to equal 2.0 atmospheres times 318.15 kelvins over 308.15 kelvins. And once again, we can see that our kelvins are going to cancel out. We're going to just be left with atmospheres, which is terrific since we're trying to solve for pressure, and atmospheres is a measurement of pressure, so that gives us an idea that we're on the right track. So once again, punch and crunch. And when you do that, you are going to come up with 2.06 and then probably some other numbers after that. Now let's talk about sig figs for this. And let me pick a different color. So we have 2 sig figs here. Now let's talk about our temperatures. What are we going to use for our temperature sig figs? Ladies, go back to your original degrees Celsius. Okay, so for our degrees Celsius, we had 3 sig figs in our first temperature, and we had 3 sig figs in our second temperature. All right, so 2, 3, and 3. That means that our final answer is going to have 2 significant figures. So underline, look behind. And so that's going to have the final final pressure at 2.1 atmospheres. All right. Now, once again, let's check to see if this answer makes sense. So we're saying pressure 1 is greater than pressure 2. Now, in order for that answer to be sensible, to be reasonable, that must mean that temperature 1 was greater than temperature 2. Let's check that out. Was temperature 1 greater than temperature 2? Yes, it was. So this answer of 2.1 atmospheres is a very reasonable answer for the numbers, for the measurements that we have. All right, and then let's do it all over again using our other formula of pressure 1 times temperature 2 equals pressure 2 times temperature 1. All right, so pressure 1 times 308.15 kelvins equals, let me scroll over a little bit more, equals 2.0 atmospheres times 318 kelvins. And once again, this is going to leave it with pressure 1 equals 2.0 atmospheres times 318.15 kelvins all over 308.15 kelvins. So once again, we see we come to this place where the two formulas kind of come together and are looking very similar, and that's perfectly fine. They should at some point look very similar, and once again our final answer is going to be 2.1 atmospheres. All right, so let's go back over Guy-Lussac's law. Make sure that we picked up on all the most important things from this page of notes. So first, we know that Guy-Lussac, we have constant volume in a direct relationship between pressure and temperature. As pressure increases, temperature increases. As temperature decreases, pressure decreases. And this is going to lead you to having a graph for Guy-Lussac's law that shows that direct relationship because it has this nice straight diagonal line. we see that temperature is graphed on the x-axis and pressure on the y. Don't forget, for Guy Lussac, just like with Charles, temperature must be in Kelvin. So you do have to do that conversion. That is something that you're going to have to memorize. We had some examples, some real life examples of Guy Lussac's law. And then we have our formula for Guy Lussac's law. And the formula is P1 over T1 equals P2 over T2. Or you can go ahead and say pressure 1 times temperature 2 equals pressure 2 times temperature 1. And don't forget our little special note on STP. STP stands for standard temperature and pressure. Standard temperature is 273.15 kelvins, and standard pressure is 1.0 atmospheres. And I do have a page in here that gives you a little summary of the laws. Now notice once again, ladies, that these laws are written how you're going to see it in most textbooks, websites, and videos. But don't forget, if for some reason you don't feel comfortable with our fractions, don't forget you can always say your formulas like this, and once again over here, P2 times T1. And here's another little visual that I have here for y'all so you can see these relationships. So if you want to say pressure, volume over temperature, okay, and what we see at the top, this is Boyle's law, where we have an inverse relationship between pressure and volume. Then over here on this side, we have Guy Lussac's law. Okay, so there's Guy Lussac. And last but not least, we have Charles's law. And Charles is volume and temperature. And for Guy Lussac's law and for Charles's law, we have a direct relationship. Boyle's law, we have an inverse relationship. So ladies, if you can memorize this page right here, if you can take that information and know what is direct, what is inverse, and you know what the graph is going to look like, what's going to be graphed on the x-axis, what's going to be graphed on the y-axis. This is the main points of all three of these laws. Now, your ability to apply them to real life situations is always going to be very helpful on many multiple choice questions that you would have on a test. But the real heart, the real meat is going to be in your ability to know which variables are in which law, what their formulas are, and the type of relationship that you have in between them. All right, so then your assignment for today is going to be a worksheet that you have that has both Charles's law and Guy Lussac's law on it. You do have 2 Flipgrid videos to do. You're going to do one Flipgrid video on Charles's law. Then you're going to do the other Flipgrid video on a Guy Lussac law problem. And I'm trying to think. I think that is everything that you need to know. If you have any questions, please feel free to email me. Y'all have a great day.